13 is kinetics. Kinetics talking about now the pathway of the reactions rather than just the state function beginning and difference. This is a famous equation related to kinetics, the BZ reaction, where it produces all these cute little swirls in it and it just keeps going, where it produces a lot of intermediate compounds, and it has like 5 steps to its mechanism. And these words, of course, don't really mean much to you right now, but later on we're going to go back and take a look at it at the end. I did put a link in here for a little video showing the reaction taking place, and a web page you can go to look at the reaction where they're documenting the different rates of the different intermediates and things. But this is a very famous kinetics reaction. So I wanted to show that to you. Like I said, at the end we'll come back to it after we've kind of gone over a lot of the vocabulary, so you'll have a better idea of what I'm talking about. Alright, so learning targets, lots of learning targets. Some of this in the beginning will seem like review of last year, because collision theory will be talking about that, how to speed up a chemical reaction, and if you increase the temperature, of course, decreasing the temperature is going to slow down the reactions. The opposite actions will occur, talking about activation energy and its importance in kinetics, and looking at the potential energy diagrams. We'll be looking at those in the beginning part of the PowerPoint, and then we'll hit the other learning targets as we go through. So for reactants to form products or collision theories, the first thing is particles have to react or have to collide. Second thing, they have to collide with enough energy, and we call that energy amount that's needed for the reaction to occur the activation energy. So that's an important term to write down, the activation energy. And then, of course, is the orientation. So the relative orientation, the way the particles are aligned, they have to hit in the right angle or side of the molecule for bonds to break and for bonds to form. So if the reacting particle doesn't collide at the correct side, it will just bounce right off and go the other direction. So we'll take a look at an example of that in just a minute. So, looking at an example of orientation here on this particular slide, the top collision is called an effective collision because it actually has a bond break and a bond form, and you get new substances, reaction occurs. The bottom one is depicting an ineffective collision. So let me show you what you're looking at here. The green, of course, is representing a chlorine atom. This is chlorine, that's nitrogen, this is oxygen, okay? So if the chlorine hits on the side where the other chlorine is, now you have a bond forming. Okay, so the bond is forming. You also see here, there's going to be a bond that's breaking. And then we result in having chlorine, new copier of nitrogen monoxide. So because it hit the side that had the chlorine, they were able to form a bond, break the other bond, now you have a reaction. That's an effective collision, so that's the correct terminology. You want to make sure that you know and write down effective collision. Down below, you're seeing here, now the chlorine is hitting the side of the oxygen rather than the chlorine. It still bumps and hits it, but no bond forms there. So it just completely bounces off and goes the other direction. And of course, this would be known as an ineffective collision, and no reaction occurs. So activation energy, the minimum energy required to initiate the chemical reaction, get it started. And some things have quite a lot of activation energy needed. Other things like, say, very flammable substances, all you really need is a spark. That activation energy would be very minimal. So it really does depend on the reaction the reactivity of your reactants, the strength of their bonds. There's lots of things that go into how much activation energy is required to get the reaction started. So things with stronger bonds that are harder to break obviously would require more energy than things that had weaker bonds that were easier to break. Now looking here, we have to go back and look at our potential energy diagrams. Before we focused on delta H and the reactants and the products, the state function stuff where we were just looking initially what we had, final what we had, and subtracting. Now we're going to be investigating more of the hill area of the potential energy diagram. So we'll be focusing more this particular area where we have bonds breaking, bonds forming, intermediates, bunch of stuff occurring. Same thing though, exothermic, you have your reactants here, products here. For the endothermic, reactants are lower, products are higher. You still have your delta H's. This is a positive delta H, whereas over here, the delta H would be negative, products minus reactants. And the last thing that's now important that we are going to label and care about is the activation energy, which always starts at the reactant line and goes up to the top of the hill. So here, the reactant line to the top of the hill, and so forth. So take a moment to reacclimate yourself to the diagram. So here, looking at the reaction of the BRNO, right here, I'll write it in darker so you can see it. There's two of them, those are your reactants. And then over here in the products, we get two nitrogen monoxides and bromine as your other product. Now, on the left side here, I want you to draw it in so that you can label everything. The reactants, the products, the transition state, also known as the activated complex. So this area, the hill, this is your transition state or activated complex. This is really the pathway, the mechanism, the intermediates being produced, the bonds breaking, the bonds forming. That's what we're focusing on now for kinetics. The pathway is important for kinetics, so we'll be looking at that aspect of the chart rather than just looking at the reactants and products and the overall exchange. So of course here is your reactant line, here is your product line. The difference between the two still is going to be your delta H. In this case, this is a negative delta H because it's an exothermic. And our activation energy is right here. Activation energy is labeled as E with a little sub A. Now, I like this diagram and also the particular model representation of it here. So if you're looking over here, this is the oxygen, the nitrogen, and the bromine. And there's, of course, two of them. Shows you the bonds. And over here, you know, this is at the reactant stage. When we get to the transition state where we have the reaction starting to take place, it shows you dotted lines. These dotted lines showing you kind of an unstable intermediate state. So what we see here, these two, their bonds are breaking. And then of course here, we're seeing the bond forming. Yes, this drawing would go on the right side. Yes, with the little particular diagram. The dotted lines, of course, is showing bond breaking, bond forming, and then you have intermediates. You know, sometimes species in between that are very unstable and, you know, can be fleeting very quickly, are going to, you know, try to bond with something to become stable again. And that's where we get the new substances out of it. But that's why the hill there is such at a high energy, because that's where we've got really high energy state, bonds breaking, bonds forming, and lots of unstable entities in the reaction at that point. Down here, what you'll see over here now is we have our two NOs right here, and then our one bromine as the product. New substance is formed from the reaction. Any questions on looking at the potential energy diagram from the transition state perspective, the hill perspective, what's going on there? So all good with that? Now this is another example of a potential energy diagram from your textbook, showing a reaction of the this particular reactant changing over into this particular product. I like the representation too because it also shows some of the instability, because in this particular instance, the molecule itself, the bonds have to bend and stretch a little bit, which of course creates a lot of the instability. That's why we're at a higher energy state. And as you can see here, there's another dotted line representing an intermediate substance, intermediate entity. And it actually flips over to establish the CC bond. So the molecule itself bends and flips over. But it's at a much higher energy state at that point because it's unstable, achieving then the product now where the molecule has the new bond with the carbon on the carbon-carbon bond, rather than when initially it was the carbon-nitrogen bond to begin with. I like that. Shows another activated complex forming, showing bending, showing intermediates, showing high energy state. All right, so now we're going to go revisit how to get a date for the dance so we can recall things that will speed up chemical reactions. Okay, so now that we've seen the video, let's go over, because really there's only 4 things that actually affect the rate of reaction, but there were 2 ways to manipulate one of them in the video here, so let's talk about them. Things that increase the rate of reaction. A higher temperature. And what was the analogy in the video of the higher temperature? Cutting the time in between classes. Yes, so you have to run the class, so you're moving faster. Higher temperature, of course, makes the particles have more kinetic energy and are moving faster. So that would increase collisions, okay? The second one is a high concentration. This is the one that was manipulated in 2 different ways, because concentration is a measure of what? Moles per liter, right? So moles over liter. And in the video, what was the analogy for manipulating the moles part?
Adding more students.
Adding more students, adding more particles, obviously, is going to increase your concentration. What was the analogy in the video for the volume or the liters?
Making the hallways smaller.
Making the hallways smaller, yes, so they have less space to move around in. That would also increase the concentration as well and cause more collisions. The next one, smaller particles, greater surface area. And what was the analogy in the video for this one? No traveling in packs, yes. That is definitely what we would do. Take crystals and you can grind them up, make them smaller, or rather than just like throwing a chunk of metal in there, you could use like iron filings rather than just, you know, a big block of iron or so forth. That would increase your surface area and get the particles to react faster. So using more powdered, granular stuff versus chunky, larger pieces. And the last one was adding a catalyst. And what was the analogy in the video for that?
Matchmaker.
The matchmaker, of course. Aligning the particles in the correct orientation, which lowers the activation energy and lowers the hill basically. The amount of the hill gets decreased by adding the catalyst, and that of course will speed up the chemical reaction. Alright, reviewing the Maxwell-Boltzmann distribution too, because in regards, this graph may pop up. We looked at it in gas laws, but it may pop up here in kinetics because they use it to show the activation energy with the dotted line here. See, this is the activation energy, EA. This is represented by the dotted line. And showing the distribution, of course, the average kinetic energy of the particles would be the center of the bell curve here. But as you can see, the fraction of particles that actually meet the threshold of the activation energy is still small, even when you increase the temperature. So when we're thinking of chemical reactions, there really aren't a whole lot of particles in there that have enough energy to meet that activation energy threshold. So increasing the temperature a lot of the times helps move more over into that particular area. And so you might see a Maxwell-Boltzmann distribution in this particular unit for the multiple choice where they're referring and talking about the activation energy. All right, so moving on to part 2 now. We're going to be looking at differential rate law, calculating product formation, disappearance, and appearance. We're going to look at initial rates, what it means to be a zero-ordered, first-ordered, or second-ordered reactant, calculating reaction order, and solving for the rate constant, which is a lowercase k, different than equilibrium k, which is a capital K. So keep that in mind. So there's a lot of good new terms in this section, lots of new stuff to focus on. All right, so looking at this diagram, showing a reaction vessel where you have a reaction of reactant A turning into product B, like so. But one thing you'll notice here is that they give you times now, taking place over a measure of time. And as you can see, we have 0.54 moles of A left at 20 seconds, where 0.46 moles of B have been created or generated from the reaction. And then as the time goes on, 40 seconds here, you can see you have a little bit more changeover, more blue, less red. So we'll be looking at and calculating the initial rate, which would start at time 0. We'll be looking at average rates, which could be taken along any place along the reaction time. And then, of course, there's the instantaneous rates. There's 3 kind of rates that you can look at in terms of what's taking place for the reaction. We'll be using most of the time initial rate, starting at T0. Now, reaction rate, the change in concentration of a reactant or product per unit time, is the definition of what we're looking at here in terms of general reaction rate. Like I said, there's initial rate, which one of your times starts at 0. Concentration at T0, of course, is your initial concentration. We'll be looking at average ones where you can take them along any point along the reaction curve. So we'll be looking at those. There is a formula for it. All right, so average reaction rate, we use the concentration of a particular chemical species at the second time, subtracting the concentration of the species at the first time over the change in time, basically. Now, we're looking at, of course, reactants are going to be rates of disappearance because they're being consumed. And then, of course, products we're looking at as a rate of appearance. And what you'll notice here in our reaction from the vessels from before, the A going to B. Of course, our reactant is disappearing, so reactant rate equations are always going to have a negative out front. For the reactants, there has to be that negative sign out front because your change in concentration, the reactant concentration should be decreasing. So finus minus initial is always going to give you a negative value, and rates can't be negative numbers. So that this sign out here up front ensures that you're going to end up with a positive rate of disappearance. And then of course we're looking at B over here. B is appearing, so you don't really need any sign up front because you're going to get a positive rate out of the subtraction anyways. So this generalized equation can be used for any chemical species that you want to plug in for A here. Any reactant or product you can calculate using that particular equation. Just know that if it's a reactant, you need the negative out front in order to change it to a positive rate, because rates are always expressed as positive quantities. And most of the time, your rate value is going to be in molarity over some kind of time unit, and it's usually going to be seconds or minutes, because these things don't take very long. So you're not usually going to see a reaction rate expressed in hours or anything like that. Most of the time in seconds, sometimes in minutes. All right, now, here is showing you data, and you're going to see lots of data charts in this unit too, which shows you times and concentrations over time. This particular one's showing the reaction of nitrogen dioxide forming nitrogen monoxide and oxygen. You have a time column here. Okay, you have your reactant, okay, and your two products. Now, I want you to talk with your fellow classmates investigating trends in this data set. And don't just go necessarily with the generalized, it increases. Well, let's look a little bit deeper at the numbers and pay attention to the numbers. So I want to see what you can come up with and conclude about this data set in terms of rates. Okay, so some things that you did notice, I heard in the discussion, yes, as time is going on, you see the concentration of the reactant, starts to steadily, it's decreasing, but it decreases at a, slower as you go down. And then of course the same thing's happening with the products. They're increasing as you go down. They're going to increase. These are decreasing. The reactants are, but as you go down, you see it's not much of a change. 6.2, 6.6, 6.9, slowing down. The reaction is slowing down. Now, why would the reaction be slowing down?
Because there's once molecules to collide together in the reactant.
When the reactants are being consumed, then there aren't as many of them there, not as many to collide. So as you can see, that would be a very good reason why the reaction itself starts to slow down. Now, also, the rate of the NO compared to O2, some people were seeing this relationship here. And you could also compare it to the rate of disappearance of your NO2, 0.0079, 0.0021, and then 0.0011. Those concentrations match the what? The concentration of the NO2 decreasing, the concentration of the NO increasing is approximately the same, right? And that would be because why? If you look at the balanced reaction, what do we have here? 2 moles of NO2 creating 2 moles of NO. So if the moles of the NO2 is disappearing, it should be equivalent to how much of the moles of the NO is appearing, right? And then if you look at the oxygen now, what's the mole ratio of the oxygen in the balanced reaction? It is 1, so its concentration should be half of the NO, because you're only creating 1 mole of that every time the reaction, runs. So if you look at the concentrations, you will see the same, you know, mole ratio in the set of data here. That's something that you should notice about the data. And this, of course, this unit has lots of data sets in it because kinetics really is all determined based on experimental data. So you're going to be seeing lots of data tables like this when you're doing your problems in the problem set. All right, now looking at the graph, we've looked at graphs like this before, back in equilibrium, except for here, we're really just looking at it in terms of rate. So the green line up here is the NO2, the blue line is the NO, and the red line is the oxygen. Anything you notice about them represented in the graph? Because these make very good multiple choice questions, of course. Which one is the product? Or which ones are the product? And how would we know which ones are the products? Which ones are the products? NO and O2, because those lines are increasing, yes. So what should you notice about their slopes? Slopes are relative to their what? Mole ratio. Again, the O2 slope is a little less steep than the other two, even though the NO2, yes, is a -1 and NO is a +1, but they're like double in terms of steepness of the oxygen. So you can read that off of the graph. And we're going to look at another one later on with instantaneous rate, but you can plot along any point of the curve here. You can plot and do the instantaneous rate, which is basically drawing a tangent line and taking 2 points on the tangent line and calculating the instantaneous rate.
Is that what that triangle is?
That's what that triangle is there for, yes, is being able to do those 2 points on the line. And that's really taking a derivative if you're familiar with calculus. But what you would notice here at this point, and this point, they are all the same exact instantaneous rate for each of the chemicals when you do your calculation. So lots to interpret looking at the concentrations versus time. There's going to be lots of graphs in this unit to look at and interpret. Now, for reaction rate, when we do not have one-to-one mole ratios, we have to take into account the extra moles of something being consumed or extra moles of something being produced. So, the generic equation up here, of course, A and B are your reactants, okay? And of course, the concentration of A, now the coefficient is 1 over the coefficient. Don't forget that negative sign out front because the reactant is disappearing. For B, same thing, you have the negative concentration of the chemical species, but it's 1 over the coefficient there in terms of calculating the reaction rate. Now for the products, it's just like before, except for now we're taking into account our coefficients again. And both of the products are appearing, so they already have positive changes in concentration. Therefore, you're going to get your positive reaction rate value. Now, I'd like you to, of course, do the example now and write out how they would look to compare all of the chemical species when hydrogen iodide breaks down into hydrogen and iodine. Our reactant here is going to be -1 over 2. Change in the concentration of HI over change in time. This one for the reaction rate has a coefficient of 1, so really it's just the change in the hydrogen over the change in time, the hydrogen concentration, and this one, the change in the iodine over the change in time. Now, they're all equal to the reaction rate at the same change in time. So you can have information about the reaction, you know, maybe information about the HI, so you can figure out the information or the concentration of the hydrogen, or calculate the concentration of the iodine at that point. So these are useful equations. Also useful thinking about it in terms of mathematical trends. Okay, we'll be looking at it on the graph again and comparing it to the mathematical equations so that we're phrasing it correctly. Like this, looking at our Haber process, nitrogen plus hydrogen giving us ammonia. Obviously, what's happening here with our hydrogen? It's decreasing, it's a reactant, so it should be disappearing, correct? So, as the reaction progresses, the concentration of hydrogen decreases. Now, what's going on with our nitrogen here? It's also a reactant, so it should be disappearing. So, as the reaction progresses, the concentration of nitrogen should also be decreasing. Now, this is the fun comparison, and you have to think about it. How does the rate compare in terms of nitrogen? So hydrogen to nitrogen. Think about it for a second. So make sure that you're phrasing it correctly and referencing the correct one in terms of nitrogen now. So we're focusing here. How would you say that as the reaction progresses, the concentration of nitrogen decreases at 1/3 the rate of the concentration of hydrogen? Now, like I said, they'll put the graph in as the multiple choice question, but they can reverse their statement to confuse you, of course. But mathematically, I'm showing you over here too. They're both decreasing because they're both reactants, or disappearing because they're both reactants. So they have the negatives in front. But as you can see, the 1/3 of the hydrogen is equal to 1 of the nitrogen. So keep that mathematical relationship in mind as you're looking up here. Now, if we're going to compare the NH3 to the nitrogen, take a look at that. Think about that one. How would you phrase it completely? We're looking at both of them in terms of nitrogen. So here, if I wanted to compare the ammonia to the nitrogen, how would we phrase that?
N2, the rate at which N2 decreases 1/2 what NH3 increases.
Correct. That's exactly how I would say it too. As the reaction progresses, the ammonia is increasing. So what was that going to look like? How does the rate increasing compared to nitrogen? So here, as the reaction progresses, the concentration of nitrogen decreases at 1/2 the rate, the concentration of the ammonia increasing. This one, how does the rate of the hydrogen decreasing compared to the rate of the ammonia increasing? Well, we can look at it from either perspective. You can compare the hydrogen to the ammonia or the ammonia to the hydrogen. So if we're looking at it from this perspective of talking about the ammonia first, the ammonia is increasing at 2/3 the rate that the hydrogen is decreasing. So you do have to do a little math there. I kind of showed you in the equation where you have to put the moles on the other side in order to get the ammonia by itself. So 2/3 the hydrogen decreasing is going to equal the ammonia. Or you might have done it the other way, where as the reaction progresses, hydrogen decreases at 3/2 the rate of the ammonia increasing. Once again, you have to flip the 3 over to the other side so that you're isolating the hydrogen by itself. Any questions on this? So far, pretty easy?
Say hydrogen increases at -3/2 the rate.
Well, the hydrogen's decreasing, the other one's increasing, yes. Okay. All right, just putting this up here as a little lead into our lab, because we're going to be using the spectrophotometers. In this particular reaction, the hydrogen iodide breaking down into hydrogen and iodine. Iodine is a colored solution. It's purple color solution. So we'll be, finding our wavelength. Now in our particular lab, what we're going to be using is food coloring. I haven't decided which one we're going to use. Last year we used like red 40 or something. But we will be creating a calibration curve just like we did for the copper lab. We will be taking our colored solution and we will be adding bleach to it, and then we'll be taking data absorbance about every 5 seconds of the fading of the color, so you're going to get the reaction time. You can use Beer's law, of course, then to transfer all of those absorbance values into concentrations and create your graphs from that. But going back to the idea that we will be using colored solution, so we will find the designated wavelength that absorbs best with that colored solution. Might use blue, might use green this year. I don't know exactly which color I'll choose, but we have quite a few back there to choose from. But that's going to be kind of what the design of the lab is going to look like. All right, now instantaneous rate. The value of the rate at a particular time can be obtained by computing the slope of the line tangent to the curve at that point. And the instantaneous rates will be the same for different species at the same time. So this is really, picking a point, drawing the tangent line, finding the slope of the tangent line is the instantaneous rates, also basically the derivative. Okay, so here looking at this reaction, they're showing the species HI here, and this one is H2, concentration of H2 and concentration of HI. But I like this graphic because it's showing right here this particular point, the hydrogen, of course, is being consumed and disappearing. The HI is appearing, but the tangent lines drawn at those particular points calculating instantaneous rate. What you should notice, is that they are the same value at those particular same exact moments. Now, the instantaneous rates along the curve, though, are going to be different as you go along the curve. So if you chose a different point, that instantaneous rate, but if I chose right here and right here, that instantaneous rate will not be 0.0070, but those 2 points still should give you the same exact rate. Types of rate laws. There are two types of rate laws. And in the rest of this PowerPoint, we'll be looking at the first one, differential rate laws. The second set of PowerPoint notes, second lecture, is on integrated rate laws. And really, it's not too much difference going on here. Differential is a comparison of the rate versus concentration. So rate versus concentration. Rate and concentration are compared, whereas integrated, we're looking more at the concentrations and how they look in comparison with time. So two different ways to look at the rates. Now, the integrated rate laws all have equations that are in formulas that are on your formula sheet. Differential rate law, you really have to look at the data and calculate it from the data to figure out the rate law. Okay, so let's look at the setup and the notation for what a differential rate law looks like. Shows the rate depends on the concentrations of reactants. So if we're using this example where nitrogen dioxide is decomposing, what you're going to see is an equation that looks like this. It's going to be rate equals the lowercase k, which is the rate constant, times the concentration of the nitrogen dioxide, because we only look at the reactants and their disappearance in the rate laws. And it's going to be raised to some power n, which is called the order of the reactant. Now, I'm going to show you how to find that number n from the experimental data. Later on, we'll have examples of how to find that order of reactant. But one thing I'm going to state throughout is that n value has nothing to do with the balanced reaction. Has nothing to do with the moles in the balanced reaction. It is figured out only based off of the experimental data. So keep that in mind. I'm going to say that again, over and over again. But you need the correct notation. It's going to be rate equals K times the concentration of the reactants raised to a certain power. And if there's more than one reactant, there'll be the N and the M, which are different orders of reactants for those particular reactants. So this is the notation of the differential rate law. We're going to figure out how to find it now. All right, so Concentrations of the products do not appear in the rate law because the reaction rate is being studied under conditions where the reverse does not contribute to the overall rate. So we're really just looking at the forward, and you're really looking at it from an initial rate standpoint, the initial disappearance. So usually you'd be collecting data from the initial rate values. Now, the value of the exponent n must be determined by experimental data or a proposed mechanism, which is another method we'll do at the end of the PowerPoint. But you cannot use it from the balanced reaction. Do not look at the balanced reaction in order to figure out the order of reaction. Experimental data only, finding the order of reactant. Now, in order to find an overall reaction order, it's very simple steps. Basically, if you have more than one reactant in there that are raised to different orders of the reactants, you simply just add them together. So the number and the exponents added together ends up being your overall order of reactant. Overall order of reaction. Now, up here I'm showing you an example where the reactant A and the reactant B are both playing a role in the reaction rate. They both have their own reactant orders. Of course, we have the rate constant, lowercase k. But really, in order to find the overall, all we have to do is add n plus m. So I want you, after you take a look at this, look at the example. It's very simple, easy. Figure out the order, overall order of the reaction. Here is our example where we have a reaction A plus 3B equals C plus 2D. Our reaction rate law here is rate equals K times the concentration of A to the second power and concentration of B to the first power. So the overall order would be basically 2 plus 1 there gives you 3, the overall order of reactant. Not hard, that part's right. So starting with the method of initial rates, just to kind of go over what we're going to be looking at here, a series of experiments that are conducted with different concentrations and they're measuring the initial rate. That means the first time is always time 0. Okay? And we'll be looking at this data table of information in order to figure out the order of the reactants for the overall reaction. So they're carried out using the different concentrations you'll see. And of course then you'll see that the results are we're looking at comparing the rate depending on the initial concentration of each of the reactants. So when we do the calculations with our experimental data, you'll be able to tell what order of the reactant it is. So to review real quick, a 0 ordered reactant is when you change the concentration. You can double it, you can halve it, you can triple it, but the reaction rate is going to remain the same. So nothing actually happens here. So once again, to abbreviate this one, we call this one the no change. Doesn't matter what you do to the concentration, your rate remains the same, the no change. First order reactants, of course, for instance, whatever you do to the concentration is exactly the same thing that happens to the rate. So if I double the concentration, the rate is also going to double. If I half the concentration, the rate is going to, half, so forth. So anytime, anything that you make to the concentration, that will affect the rate in the same way. So we call this one the same change. The second order reactants, going back over them. This is one where you double the concentration, the rate is going to quadruple. So we call this one square of the change, basically. So if I triple it, then my rate's going to go up by 9, because it would be 3 squared there. So we call this one square of the change. And if you can remember no change, same change, square of the change, it becomes pretty easy you to look at these different order of reactants. So, tripling concentration multiplied by 9 for the rate. Now, looking at an example like this, these are very, something like this would be good multiple choice questions, okay? They would give you, a list of possible answers, and you'll have to pull from that same bank in order to answer the multiple choice questions. So take a moment. Looking up here, they give you a little bit of information. Read through the questions, and then we'll go over the answers in just a minute. All right, so we're writing out the rate law. First thing you write out, of course, is rate equals. Then what comes next? K, the rate constant. Now, it says A is a first order reactant, so you're putting in the concentration of A. Technically, yes, it's raised to the first power, but that's like a given, so you don't necessarily write that in. Just like in math, we don't put 1x, we just put x. Now it says B is second order, so what am I going to do to the B concentration? Square it. And then it says C is 0 order.
So you don't include it.
So I don't include it, thank you. That's exactly right, because 0 order raised to 0 power is going to be 1, so it's not going to affect it. That's a waste of time to write it in there. All right, what will happen to the rate if you quadruple the concentration of A? It is also quadrupled, or 4 times the rate. Okay? Yes, because that is a first order reactant. It is a same change. What will happen if you cut the concentration of B by half?
Then it will be quartered.
Okay, so if we are cutting it by half, so it's going to be 1/2 what? It is a second order, so it's going to be square of the change. We're having it, so
One quarter.
so it'd be 1/2, raised to the second power. So yes, it ends up being 1/4 of the rate. 1/2 times 1/2. We're square of the change here.
Wait, 1/4 of the rate or raised to the 1/4 power?
No, it's 1/4 of the rate.
Okay.
So it's the change squared.
Oh, okay.
Very good. All right, next. What will happen to the rate if A and B are both doubled?
Then it'll be multiplied by 8.
It will, because A will be 2 times, and then B is going to be 2 squared, square of the change. So this results in a factor of 8 times the rate. What will happen if C is increased by a factor of 10? No change, because obviously this one's a 0 order, and by definition you can do anything to the concentration, it will not affect the rate. What will happen if A is quadrupled and D is cut in half?
Nothing, because they cancel each other out.
Also, yes, this would be 4 for quadrupled. Once again, this is going to be 1/2 squared for the second order, which turns into 1/4. So, and basically 4 times 1/4 is 1 times, which is really no change in the rate. Good so far? All right, now we're going to be looking at a specific reaction here that has the data table along with it. We have bromate plus 5 bromide plus 6 hydrogen, giving us bromine and water, this big redox reaction up here. And we want to determine the order of the reactants for each of our reactants in our balanced reaction up here. Now, once again, we're not looking at the balanced reaction for the order of reactant. We have to look at the experimental data provided. And then we're going to be able to find the order of reactant for bromate, the order of the reactant for bromide, and the order of the reactant for hydrogen, which is represented by the P there. Now the key is, and just so you know, I put a little note there, but there is space at the top of the next page that you can use in order to write out the experiments. So looking here, you're going to see a lot of this in your problem set where you have these data tables that give you different concentrations. These are initial concentrations, and they're measuring the rate at those initial concentrations. This is that initial rate method. And we usually label, or they're labeled experiment 1, 2, 3, 4 over there, so that you can figure out and look at which experiments you want to use in order to figure out the order of the reactant. Now for bromate is where I'm going to start. I'm going to start with the first reactant here. I need to look at the data and figure out what two experiments have only bromate's concentration changing. Where is it only that bromate is changing? Hydrogen and bromide are staying the same in terms of their initial concentrations.
The second.
Where is one that bromate's the only concentration? Two experiments where the bromate's the only one changing. We need two experiments.
Oh.
1 and 2. If you look at experiments 1 and 2, bromate's at 0.1 and 0.2. If you look at the other reactants, they are the same. They are both 0.1s for both of those experiments. We only want the bromate's concentration to be the one that's changing. Now what we can do is use our rate law equation to calculate what the order of the reactant is. So in general here for the rate law for bromate, rate is going to be the rate constant times the concentration of the bromate, raised to the order of the reactant N. So we're going to use this generalized setup. What I always do when I'm figuring this out is I use the larger concentration. I put that experiment on top, so I get whole numbers out of it. So I'm going to put experiment 2 first over experiment 1. And the rate for experiment 2 is 1.6 times 10 to the minus 3. The rate for experiment 1 is 8 times 10 to the minus 4. Now the K's of course will be the same because it's the same reaction here, same rate constant. And then the concentration of the bromate in experiment 2 raised to the nth, and then over here raised to the nth. Now what you'll notice, and I typically don't write in the K's because they end up canceling out anyways, so they're the same value. Now it's a simple, easy math. If you look here, we can use our exponential math, move this over, make this 16 times 10 to the minus 4, right? So what's 16 divided by 8 then? So this is 2. What's 0.2 divided by 0.1? 2. So 2 to the nth power equals 2, and must be 1. So for bromate, the order of the reactant is going to be a first order. This is for bromate. The order of the reactant is 1. Now, I want you to go ahead and try to do bromide and hydrogen on your own. Pick some experiments, see if you could figure out the order of the reactant. Sure.
Why didn't we write other concentrations in the rate law equation?
We could write those other ones out, but they would just cancel each other out. Because 0.1 over 0.1, 0.1 over 0.1. So you can do that. We're isolating the bromate. Everything else is the same. So really all we have to focus on is the numbers that are affecting the bromate. Make sense? For bromide, which experiments do I want to focus on? 2 and 3. If you look at 2 and 3, they're changing. The other two are staying the same. Very good. So then you just set it up. Okay, this is for bromide. And once again, now, like the K's, you don't really even need to care about. Drop them out. So basically, it ends up being 2 equals 2 to the m. So what kind of reactant order is this one? Bromide is reactant order first as well. Okay. And last but not least, let's look at our hydrogen. What experiments do we want to use for hydrogen?
1 and 4.
1 and 4. So yes, it's not always obvious right next to each other. As we look here, then we do 3.2 times 10 to the minus 3 over the 8. And then we have our 0.2 over 0.1. These are raised to the p. Now, once again, doing the easy math, move this over, make this minus 4. 32 divided by 8 is 4. So 2 to some power equals 4. P is going to be 2. So if we're writing out the rate law now for this particular reaction, the rate equals K times the concentration of the bromate times the concentration of the bromide, which are both first order, times the hydrogen, that is second order. That would be the official rate law for this. Now if I asked you what is the overall order for this particular reaction, what would you say? 4, because you would do 1 plus 1 plus 2. So the overall reaction order would be a 4. Good so far. Now let's talk about units of K. On the AP exam, you're going to calculate K, but the way that they usually break it up is they have a 1 point for the calculation, 1 point for the units. For some reason, they really care about making sure you get the rate constant units correct. It's this basic formula here. 1 over the molarity, the overall reaction order minus 1 times the time. That's a generalized way that you can figure out the order very quickly. Now you could set it up and cancel and figure out the M's that way, the molarity that way, but it takes a lot of time. So if we were doing the last reaction, where we were doing the bromate, bromide, hydrogen, we would just do 1 over m to the 4 minus 1. And I believe the time was in seconds, so you would put the time in seconds. Usually what you're going to see in the data table is that time is in seconds or minutes. Because these things happen quickly, you're not going to usually see a time measured in hours for reactions. Just saying. Okay. Now, this ends up being 1 over m to the 3rd times the seconds. Other ways it can be written, though, that you might see it. You might see m to the minus 3, s to the minus 1. They like to write it like that. Now then is 1 over moles to the 3rd over liters to the 3rd times the s, right? So then, yes, if we're flipping them, it'd be liters to the 3rd times moles to the minus 3. Is that right? S to the minus 1? There we go. Yes, we've rearranged it correctly. Yes, so sometimes they write it like that, and usually, actually, it really would be moles to the minus 3, liters to the 3rd, s to the minus 1. Like that. They always put the moles first. Sometimes they'll write the units like that, and it's confusing, but just realize the moles and liters are just going to work out to be molarity, because we're talking about concentrations, of course. All right, now moving on to mechanisms. Mechanisms are fun. Sure.
Is it possible to have an element or a molecule that has an overall order of 0? Like every molecule of the reaction has an order of 0.
I suppose I've never heard or seen one like that, but I guess there probably are some out there where it doesn't matter what you do to the concentration, the rate's going to be the rate's whatever it's going to be. I don't know. Yes, I'm sure that's a possibility. All right, so mechanisms. We're going to be looking at mechanisms, and you'll be able to determine reactant order and overall reactions and stuff based off of the proposed mechanisms. We're also going to define intermediates and how the catalysts appear in the mechanisms, and propose mechanisms interpreting potential energy diagrams with multi-step mechanisms. So first of all, what is a reaction mechanism? Well, it's the steps by which the reaction occurs. Elementary reactions, or ones that we say are elementary, they only have one step. They occur in one collision. There you have it, one step. Now, if we're looking at the elementary reactions, the one that happened in one step, we can determine the molecularity of the reactant. And it's defined for you over here in the chart. A unimolecular reaction really is going to focus on having only one reactant that has a reaction order of 1. Is a first order reactant, and I believe that would be something would be decomposing and of the nature if you're starting out with a single reactant like that. So the unimolecular would be determining the molecularity of that one. Now there's two options that are bimolecular. You see where they have overall reaction orders of 2, where one example is showing the collision between the same reactant, like A and A collide with A. But you could also have another version of a bimolecular where you have 2 different chemical species. A is colliding with B to create the reaction. Now, the termolecular ones are very rare, and this is why, and you have these options where you have to have 3 different reactants all colliding together to make the bonds break and bonds form. So that's why they're rare. Usually it's 2 things hitting each other or just one thing decomposing. You don't usually have 3 things hitting each other. Now, it occasionally occurs. That's why they define it for us. But you can see different options of it. Be A colliding with 2 other A's, A colliding with A and then a B species, or 3 totally different species all colliding. You have bonds breaking, bonds forming. And it happens all in one step. Okay? Now we're going to look at the ones that do not happen in one step. The multi-step ones. Most chemical reactions, of course, occur in a series of elementary steps. And that gives us something called an intermediate, a chemical species that doesn't last very long, that's kind of unstable. And you can determine that it's an intermediate because it is produced in the first step, and then in the next step it's being used up as a reactant. So it's not going to appear in the overall balanced reaction. It is formed and then it disappears. It's used up. Formed and then used up. So you will not see it in the overall balanced reaction. However, another thing that you'll see are the catalysts in the mechanisms. They will appear in the reactants of the first step, and then they will also reappear as a product of the last step. So you see that it does not get consumed, does not get changed or altered by the reaction, and the catalyst also will not appear in the overall balanced reaction. So the catalyst remains unchanged. It'll appear in the reactants of the first or second step, or in a step, and then it will appear at the end. So it ends up canceling out. All right, so looking here, we're going to look at this particular reaction mechanism, and I gave you the particular diagrams for it. Just to define our species here, blue, of course, is nitrogen, red is oxygen, and black is carbon. So these are NO2s. This is an NO3. This is a NO. Then we have another NO3. We have a CO, NO2, CO2. Now a couple of things. When they give you a mechanism to compare to, you see the balance reaction up there. Another thing that they will give you is the rate law. In this case, they didn't give you the rate law. Instead, they told us this information down here, the slow step, the fast step. So the first step in the mechanism is the slow step, the second one is the fast step. And from this, we can determine the rate law. So they give us the overall balanced reaction, they give us the mechanism, and tell us which one's the slow step. We can determine the rate law. But before we do that, does anybody see up here any intermediates? Something that's being produced in the first step that gets consumed in the second step?
NO3.
NO3, so this one would be an intermediate. Right? Does anybody see a catalyst up there? Yes, if you look at our overall balanced reaction, NO2, how many moles is up here?
2. Oh, 1.
Only 1 mole. So that means, if you look at our mechanism here, we have an NO2 here and an NO2 here, where it starts out in the reactants, it ends up in the products. It's not altered or consumed, so we can declare that one to be a catalyst. Whereas the other NO2 over here is participating in the balanced reaction. Make sense? So now we're going to look at the slow step, fast step stuff in order to figure out our rate law. So let's go ahead and define that. The reaction is only as fast as the slowest step, which is the rate determining step. The rate determining step, or the slowest step, determines the rate law and the molecularity of the overall reaction. Now there are a couple of requirements in order to use the proposed mechanism to determine the rate law, or vice versa, where you have the rate law and the balanced reaction and you're determining the mechanism. The requirements: the sum of the elementary steps must give the overall balanced equation for the reaction, and the mechanism must agree experimentally with the determined rate law. So these things have to happen in order for us to use the proposed mechanism. The way these problems are going to look, they either give you the balanced reaction and the rate law, and then they give you like a couple choices of proposed mechanisms. You have to decide which one it is. Or they can give you the proposed mechanism, tell you the slow step, give you the overall balanced reaction, and you write the rate law. So there's a couple different ways you might see these problems. Yes. What are the requirements for using the proposed mechanism to find the rate law, or given the rate law to find the proposed mechanism? So going back, identify the rate law from the proposed mechanism. The first thing you need to do is look at the slow step. And which step is the slow step? This one, the first one up here, right? Step 1. This is our slow step. So we're only paying attention to the slow step here. We don't care about the fast step. We are only as fast as our slowest, reaction. Just like you're only as good as like the weakest link in your team, same thing here. You're only as fast as your slowest step here. Then you look at the reactants in the slow step. Only the reactants. We have NO2, we have NO2 here. Looking at the reactants in the slow step. And we just count them, basically. How many NO2s are there? 2, right? So, basically, the rate then becomes the rate constant times the concentration of the NO2 squared. You count the reactants, and in this case there's 2 of them, so this is going to be second order. Now if it was, say, NO2 and CO up there, it would be the rate equals K times NO2 concentration times the CO concentration. So it's really the number of moles of the reactant in the slow step. Count them, they end up being the rate law. And that's equivalent because it's the slow step. So that's the rate determining step. So those are the ones that will be affecting the rate. The proposed mechanism way is very easy if the slow step happens to be the first step. If the slow step is not the first step, then we have to do some substituting, which I'm going to show you in an example coming along here in just a minute. Any questions about looking at the slow step being the first step in the mechanism and determining the rate law? The information that will be provided to you, if they ask you for the rate law from the mechanism, they will define which step is the slow step for you. Now let's look at exercise 3, where we have a balanced reaction, we have a rate law, and we're going to propose a mechanism here. Like I said before, though, most of the time they're not going to actually have you generate your own mechanism. What they'll usually do is give you this information and then like 3 choices. And you have to pick the right one that correlates and is experimentally okay with the rate law and with the balanced reaction. Yes. I'm proposing a mechanism based on what we have up here. And there's different ways you can propose this, but I'm going to go the simplest route. So my first step here, I only have 2 reactants here. So I'm going to have them collide with each other as my first option. That leaves in my second step what reactant to collide? I only used one of these guys, so that leaves that reactant to go in my second step. Now, looking up here at my products too, what could we propose as a possible product from my NO2 and F2 colliding?
NO2F.
I could get an NO2F out of that. Good. Now, what's left over? An F is left over. So what would this be, this F over here?
That could be another reaction.
This over here has been created. Is it stable?
No.
No. So we would call that a what? An intermediate. Thank you. Yes. So the intermediate then must become the reactant in the second step, right? And NO2 plus F would give you another NO2F, right? So this is like the simplest one I could come up with. I'm sure there's other ones you could generate that agree with the balance reaction and the rate law. However, for this one to be equal to the rate law and the balance reaction, this of course would have to be the slow step, because in the rate law, what do we have as our reaction, our reactants? We have NO2, we have F2, they're both first order. There's only one NO2 in the slow step, one F2 in the slow step, so that does correlate and agree with the rate law. In this particular case, this would be an acceptable proposed mechanism because it agrees with the balance reaction. The F's, these would cancel, right? Because they're intermediates. And yes, it also correlates with the rate law because the reactants in the slow step are at the right order of reactant, because there's one of each in the rate law. So, like I said before though, you won't necessarily have to generate a proposed mechanism on your own. What you'll be asked to do though is, here's the rate law, here's the balance reaction, here's 3 different options, choose the one that fits and explain why. So here you have it, slow, fast, and F of course is an intermediate that's going to be consumed in the second step. Now for the fun one. My favorite, of course, where the slow step is not the first step. We call this a steady state approximation example. And we have a fast equilibrium occurring. Yes?
I guess what you're supposed to do.
What are you supposed to do?
Because D is an intermediate, you just said D to A plus B, which gets you A plus 2B, so it already agrees with the reaction above, which makes it slow step.
Correct. Yes. Very good interpretation. It's a little bit more detailed in the substitution, but that's the basic gist of what you're going to do. You substitute back from the intermediate to get the reactants. So I like the idea. But let me explain to you it in terms of the substituting so everybody's on the same page. Now what you have to remember here is we have a fast equilibrium. So we have a K forward, we have a K reverse, right? The rate constant going forward, the rate constant going backwards, right? Reverse. Has equilibrium, they're at what? Equal rate, right? So the rate of the forward, the rate of the reverse. Now, just so we establish that, the rates are equal for equilibrium. The way the book does the notation, I'm going to show you their way because you'll see that in the problem set. They don't use KF and KR. Instead, they use K1 and K inverse of 1. So that's how they note it in the book, and that's how you see it in the example problems. Now, the second mechanism also has its own rate constant, right? So this would be our K2 for this particular one, going from D plus B to give you C. Each individual step, is going to have its own rate, but we're not looking for the individual steps rate constants and rates. We're looking for the overall reaction rate. So we're going to merge them all now. And yes, as stated, we're going to do some substituting now. Intermediates are not allowed to appear in the rate law, right? They're not in the overall balance reaction, so they're not allowed to appear in the rate law. So what you can do then is, make them equal each other. So we have the rate rate of the forward equals the rate of the reverse. So we're going to deal with our first step. So the rate of the forward then is going to be K1 times the concentration of A times the concentration of B. The rate of the reverse is going to be K inverse of 1 times the concentration of D. They equal each other because we know this because they're at equilibrium. Now, as suggested, we solve for D. So we're going to go ahead and move this over here. Right? So D now is going to equal K1 over the K inverse times the concentration of A times the concentration of B. And because the second step is the slow step, technically if we just were allowed to write it as is, this would be the rate constant of it times the concentration of D times the concentration of B. But because D is an intermediate, we can't leave it like that. Instead, we have to take this now and substitute it in here. We're going to substitute for D what we have over there. Now we substitute it in, and the rate equals K2 times K1 over K inverse 1 times the concentration of A times the concentration of B. And then, of course, we add on our last concentration of B here.
So B squared.
So it ends up being B squared, yes. But what I want to talk about now is this part. These are a bunch of different rate constants. And they are what they are. They are constant values. So if we're multiplying the 2 and dividing by the 1, aren't we just getting a new rate constant? Yeah, so I like to call this K nu now. Of course, your book doesn't write it as the new K. It's a new rate constant that has now been recalculated. So they drop off, or they just turn this into, they just turn it into K. I like to think of it as, oh, it's a K, but it's a new K. It's a recalculated K. So then if we're going to simplify it down, it ends up being rate equals K times the concentration of A times the concentration of B squared. That means A is the first order reactant, B is a second order reactant. And this would be what you would declare as the rate law. And if you look up there, then the rate law works for our slow step being the second step. And we have no intermediates in our rate law because that is not allowed. Any questions? There are some substituting ones. Just go and substitute it back. Realize that it doesn't really matter about the K's. It's just going to turn into a new K. Yeah, it doesn't really matter about them because they're just going to multiply and divide and become a new K. So just make them a new K and write it as K. All right?
So all that work.
Yeah, exactly. All that work for nothing.
Now, you don't have to necessarily write all of this out, but you can show me the substitution of the D is going to equal the K times the A times the B. You don't have to rewrite all the K's in there, but I just wanted to show you where the new K came from. And yes, we are correct. So like I said, I put K new here to know that, oh yes, it's a new K, but you wouldn't write that in there. You would write out just rate law equals K times the concentration of A to the first order and B to the second order. Now, if you have a multi-step mechanism, your potential energy diagram looks a tad bit different. So, this is how it looks. You have multiple hills, multiple steps in the mechanism, right? So this one's going to take place in 3 steps because I have 3 hills. So this one's going to be a 3-step mechanism. And I have an activation energy at my first step. And that activation energy happens to be lower, so that step I'm going to consider to be a fast step. And if that is valid, that the lower activation energy declares it that it's a fast step, can I figure out which one is the slow step? One, the highest hill, the highest activation energy will be your slow step. Exactly right. These diagrams, of course, make good multiple choice questions. They can ask you about how many steps in the mechanism. They can also ask you which one's the slow step. And another thing they can ask you about is how many intermediates are involved. We'll get to the intermediates in just a second. So the first step is fast, we know, because the hill is a little bit shorter, lower activation energy. The second step is the slow step. This is going to be your rate determining step because it's the slow step. And the slower step here has lower activation energy as well, so it is going to be a fast step. So the second step we would determine to be the rate determining step because it is the slow one, since the activation energy is higher. Now, like I said before, another thing to note on here, how you can determine this, the little valleys in between the hills are telling you how many intermediates you have. So in this case, we have two intermediates forming and are present because in between the mechanisms here, you have some chemical species that are formed that do not last and stick around. Of course, you could also realize that because there's three hills, there are three activated complexes, three transition state part of the mechanism here going on. Pretty easy to look at the graph and be able to determine these factors. But like I said before, they are usually multiple choice questions with these labeled. Tell me which one's the slow step, tell me how many intermediates there are, or they could ask what's the rate determining step, and they would have it labeled for you. So these make very good multiple choice questions. Now for catalysts. Substance that speeds up a chemical reaction without being consumed itself, and it provides the new pathway for the reaction with the lower activation energy. As you saw in the video, the matchmaker analogy is true where it aligns the particles better so they're more oriented and collide, and will have to collide at a lower energy. The catalysts will also appear in the potential energy diagram. Does anybody remember from last year what happens to the potential energy diagram when you add the catalyst? It lowers the hill part of the graph. You remember that? Like here, they'll show you the catalyzed pathway where the graph, the hill part, the activated complex or transition state is now lower, showing the catalyzed pathway. Remember, the pathway, of course, is the bond breaking, bond forming, intermediate steps, things happening under the energy exchange part of the hill there. Now, just a couple things about catalysts, although, you know, for the most part, don't really have to know too much, but if it's ever referred to, you will have at least heard of it. Before we get to the types of catalysts, here's looking at another distribution diagram. Also makes very good multiple choice questions, but showing how in our bell curve here, the uncatalyzed, the fraction amount of particles that have enough energy in order to react, meet that activation energy threshold, whereas over here, when you have added a catalyst, you can see that more particles are meeting the threshold, the activation energy threshold now. However, if you look, though, at both distributions, there are still a lot of molecules that do not have enough energy to react. So the idea that every single particle in a solution or a reaction is going to react is just not going to happen. Because most of the time, even to get some to meet that threshold with the catalyst, still there's going to be a lot of unreacted material. A heterogeneous catalyst, just so you know, they're not in the same phase. And one example of this, when they're not in the same phase, is when you have reactants that are all gases. Now, of course, you can't just like dump it into solution since it's in the gaseous phase. But what they do is they usually use like a solid metal catalyst where the gases can, bounce off the solid metal, and then of course it'll help lower the activation energy. It's through this process of adsorption, collection of one substance on the surface of another, and that helps, speed up the reaction for reactions that involve gases like that. Most of the time, what we think of when we think of catalysts is under the homogeneous or homogeneous category, where they're all in the same phase. So, like I have stuff in solution, I dump some more, catalyst that's the solution in there, and then it starts going. That's more typically what you see. Enzymes, of course, fall under this because they're in the cytoplasm or the solution type environment. They're also pretty neat because they can work at regular normal room temperature, and they make our metabolism work at a very low temperature. So enzymes being nature's catalyst, they're pretty cool. Last exercise, I want you to look at here and determine the catalyst here. So, intermediate,
NO2.
NO2, this one's intermediate.